Folks, this is dull and it has an enormous mass. Also, it's little, that is 3 indisputable pieces of evidence. Not too far off, right? Embroiling a supergigantic dark opening. Space can be frightening to ponder. The perils that prowl inside the tremendous scope of space can be unnerving. While this applies to the whole idea of space investigation, the one section that has forever been fascinating and frightening simultaneously is dark openings. These monsters of force have been the subject of innumerable examinations all across the globe. Researchers have been attempting to sort out exactly what dark openings truly are and what exists in them. However, every one of that changes now. Neil deGrasse Tyson recently uncovered something tremendous. Our dark opening is less gigantic than the one in the focal point of the Andromeda system, our closest large universe. So, we have dark opening jealousy. I figure we do. We at long last see what's inside a dark opening, and well, every last bit of it may very well take your breath away. So, go along with us as we take you on this intergalactic excursion and respond to one of history's most posed inquiries. What is a dark opening made of? An enormous blast creates the dark opening's mass, which is gathered in a minuscule region, creating a gravitational force so extraordinary that nothing, not even light, can escape from it. Once something is in there, it remains in there forever. These forces of energy come in different sizes, ranging from heavenly dark openings, which can be a couple of times the mass of the Sun, to very massive ones that exist at the centers of galaxies and can have millions or even billions of times the mass of our Sun. Significantly, researchers have noticed the effects of dark openings indirectly throughout recent decades, and with each piece of information we uncover, hundreds of insider secrets arise. Despite the fact that they appear so huge and strong that they couldn't possibly have a beginning story, they truly do. Dark openings don't simply exist in space, they're made. They need the remnants of huge stars that have depleted their nuclear fuel to be born. These stars go through a supernova blast, a fantastic event that marks the end of their lives. During a supernova, the external layers of the star are savagely ejected into space while the core undergoes gravitational collapse. Not all collapses are the same. If the core's mass is several times bigger than that of our Sun, the force of gravity overpowers all remaining forces, making the core collapse inward. This collapse is so extreme that it compresses the mass into a staggeringly small volume, creating an object with a gravitational field so strong that nothing will be able to escape its grasp, thus creating a dark opening. The size of a dark opening is determined by its mass. Heavenly dark openings, which are the most well-known type, have a mass ranging from a few times to many times that of our Sun. At the center of a dark opening lies the peculiarity, a region of limitless density and spacetime curvature. According to our current understanding of physics, the laws of nature break down at this point, and our traditional theories can't fully explain what happens inside the peculiarity. To truly understand the nature of singularities, we need to break new ground in the universe of material science. A peculiarity refers to a point in spacetime where certain quantities become infinite or undefined. These singularities appear in various theoretical settings, such as at the beginning of an expanding universe, ordinarily known as the Big Bang peculiarity, and within dark openings. When we study the Big Bang peculiarity, a crucial challenge arises. According to the theory, the universe began from an incredibly hot and dense state around 13.8 billion years ago, but as we rewind time toward this initial state, the conditions of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics can't fully describe the conditions at the moment of the Big Bang. Resolving this issue requires a theory that combines general relativity with the principles of quantum mechanics. Dark openings contain singularities at their centers. These are regions where the gravitational pull becomes immensely strong and spacetime is profoundly curved. According to general relativity, matter and energy that fall into a dark opening reach its peculiarity and become infinitely compressed. This concept is beyond our current understanding of physics, adding to the problem. The challenge of singularities has spurred researchers to seek a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics. Quantum gravity tries to provide a framework that accounts for the behavior of spacetime on both cosmic and subatomic scales. A theory like this could potentially offer insights into the nature of singularities and how the universe truly works. One approach to resolving the issue of singularities is the theory of loop quantum gravity. This theory suggests that at minuscule scales, spacetime is quantized, meaning it consists of discrete, unified units. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This implies that spacetime is not considered a continuous and infinitely divisible substance, but rather an assortment of discrete elements. These discrete units of spacetime are often viewed as interconnected loops or networks that represent the fundamental structure of the fabric of the universe. Within the framework of loop quantum gravity, singularities associated with dark openings and the Big Bang could be resolved. One of the key insights of this theory is that at tiny scales, the discrete nature of spacetime prevents the occurrence of infinite densities and curvatures that result in singularities in classical general relativity. For instance, with regard to dark openings, loop quantum gravity suggests that as matter collapses toward the core, the spacetime fabric becomes increasingly small. This size prevents the matter from reaching an infinitely dense peculiarity. Instead, the collapsing matter experiences a quantum bounce near the core, where it rebounds and begins to expand again. This scenario leads to the formation of a new spacetime region inside the dark opening, often referred to as a quantum dark opening or a bounce region. Heavenly dark openings are the most commonly observed type of dark opening in the universe.
Heavenly dark openings are the most commonly observed type of dark opening in the universe. They are formed through gravitational collapse at the end of a massive star's life. Once a gigantic star depletes all its nuclear fuel, the outward pressure generated by nuclear reactions can no longer balance the force of gravity pulling inward. The gravitational force becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a heavenly dark opening. As the star collapses, it becomes incredibly compact, packing a large amount of mass into a tiny volume. As a result, heavenly dark openings typically have a mass ranging from a few times to multiple times that of the Sun. Despite their mass, they have very small sizes. Their diameter is just a few kilometers, which simply demonstrates how incredibly dense they are. The immense density of a heavenly dark opening leads to the formation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the dark opening becomes so strong that any object or information that crosses it is captured forever inside the dark opening. Then we've got middle mass dark openings. While the exact mass range for middle mass dark openings is still something researchers need to examine further and refine, they are generally thought to have masses ranging from thousands to hundreds of thousands of times that of the Sun. These gigantic monsters occupy the central regions of most galaxies, including our own Milky Way. They hold significant gravitational influence over their cosmic surroundings and have a considerable impact on the development of galaxies. The formation of supermassive dark openings remains an area of active research and is still not fully understood. That being said, lots of different theories have been proposed to explain their origins. One prominent theory suggests that supermassive dark openings grow from smaller dark openings through a process called accretion. According to this idea, as matter such as gas, dust, and stars accumulates around a dark opening, it forms a swirling disk known as an accretion disk. The dark opening's massive gravitational force draws material from this disk, causing it to spiral inward and eventually merge with the dark opening. Over immense periods, this continuous inflow of matter allows the dark opening to grow to a supermassive scale. During the accretion process, large amounts of gravitational potential energy are released as the matter falls into the dark opening. This released energy powers some of the brightest and most powerful phenomena in the universe. But away from all that, there are also charged dark openings, which represent a captivating variety of dark openings characterized by the presence of an electric charge. There are two main types of charged dark openings: Reissner-Nordström dark openings, and Kerr-Newman dark openings. Each type exhibits distinct properties that are shaped by the interaction between the dark opening's charge and other factors such as spin. Reissner-Nordström dark openings are charged but non-rotating. They are described by the Reissner-Nordström solution in the framework of general relativity. The charge of these dark openings affects the behavior of their gravitational field. However, in terms of their overall structure, Reissner-Nordström dark openings are similar to uncharged dark openings. They have an event horizon, but the size of the event horizon for a Reissner-Nordström dark opening depends on both its mass and electric charge. On the other hand, Kerr-Newman dark openings are charged and rotating. They are described by the Kerr-Newman solution in general relativity. The combination of electric charge and rotation introduces unique phenomena associated with these dark openings. One of the notable effects is called frame dragging, which occurs because the rotating dark opening drags and twists the surrounding space-time fabric. Dark openings have both an event horizon and an inner